In this video series, we're going to take a look at something very exciting, and that is how images are related to matrices. So your standard picture is often not square. In fact, most web pictures you'll see to be 1280 by 720. And this is the standard HD form that you'll see for image sizes on the web. Not all images are of this size. There are obviously different sizes. It depends on whether they're square or rectangular or long and narrow. So these values, in terms of what they represent, are pixels by pixels. So this essentially means that you're going to require a matrix that is 1,280 rows by 720 columns. And the question is, what goes into these matrices? Well, there are actually three matrices that go into each image that is a color image. In a color image, you actually have three matrices representing that one image. There's one, we'll call them three layers. One layer represents the shade of red. The second layer represents the shade of green. And the third layer represents the shade of blue. Now, when you put red, green, and blue together in terms of the color spectrum, you can generate many different colors. In fact, all the necessary colors that we have in our typical photographs. The images themselves are each M by N. So in this case, if we had a 1,280 by 720 pixel image, then M would be 1,280 and N would be 720. Each pixel value in each of these layers is going to be a number between 0 and 255. What this essentially means in computer speak is this is going to be an 8-bit value. It's going to require 8 bits of storage, because if something that we know about binary is that an 8 bits can store up to 256 values that are in our standard decimal form. So 0, 1, 2, 3, 4, 5, 6, all the way up to 255. That's because it includes 0. So you can play around with these. You can look at different shades of RGB using some web applets and seeing like what a R value of 0 looks like versus an R value of 255. We'll come back to that in a moment. We're going to take each of these three layers and we're going to form a matrix. We'll call that matrix A. And A will be an M by N matrix. Now you could have an A matrix for each of these three layers. So you could have something that maybe we'll call A sub R, which is M by N, and then maybe A sub G, which is again M by N, and then A sub B, which again is M by N. So every single pixel will have three values associated with it: an R value, a G value, and a B value. Now let's go ahead and take a look at what this might look like in a generator online. So here is one such color code chart, and you can do a search for RGB color code charts and you'll find many different applications. So here right now we have R, G, and B each set to 255, and you can see that the color that we get is right now white. So if you set all of the pixel values, R, G, and B, to 255, the pixel color that you will get is a bright white. Alternatively, if you set R, G, and B to be 0, you can see that we get black. So on the 255 scale, we get bright white. On the 0 scale, we get dark black. And then we can pick values in between. So if I start to change the shade of R, I'm going to go ahead and, first of all, just play around with this R value, make this say 100. Then I get something that is kind of this crimson color. And if I set this to something more like 200, I get a lot more of the bright red. In fact, if I set this to 255, I get what's considered the standard red color. If I try to set this any higher, nothing's going to happen because there are only 256 different shades of red. If I set this back to 0 and change the shade of green, we can see what that will do. So there's a kind of a darker green color. And if I set this to 255, I get really this bright kind of, I don't know, minty green color, if you will. And now if I change the value of blue to 255, we can see that we get our standard blue. So these three colors put together can form many different combinations. If I go, let's say 180 on the blue, 100 on the green, and 50 on the red, then in that case I get this shade of blue. Now you can also change the change along the spectrum here and see what that does. Go all the way up to a red and then choose different shades of red. You know, maybe almost a light, I don't know, maybe pastel-ish, pastel pink color. You can see what those align to. Now there is associated with this a hexadecimal value, and this can be used in coding, for example, to specify the shades of R, G, and B without having to remember each one of these individual pixel values. The question that we're going to answer in this series is, how do I take an image and compress it? For example, I want to send an image to somebody via text message or via email, and the image size is of a high resolution, and I know that sending that image would require a massive file size, and if you're sending through email or text, that image may not arrive. So how does technology take this picture and compress it? And one thing that we know is that a full-size image, that a full resolution image, is often associated with highest quality. Highest quality. However, that's the pro. The con of this is large size. And then on the other end of the spectrum, we can look at the lowest resolution image, or a low resolution image. And what that will amount to is in this case, the pro is going to be that the file size is going to be small size, but the con in this case will be that I get low quality. Of course, we want probably something in the spectrum, perhaps right in the middle, where we find a nice compromise between good quality and reasonable file size. And that's what we're going to investigate next.